Greetings, welcome to the last part of this lab. That is part 5 of lab 2. It is the last problem that we're going to work out of the chapter 3 exercises before I kick you down the road to go take a look at a discussion question and then work at the assignments on your own. Okay, so this is exercise 3.18, which is the heights of 25 randomly selected female college students. So we obviously didn't pick them all from the basketball team, so I just thought I'd put that in there. It's kind of a picture to let you know you're not going to do that, okay? So let's go into our studio. I've already pasted the problem and the data set in here. So let's go ahead and read the problem. So the heights of female college students, part 1. Below are the heights of 25 female college students. The mean height is 61.52 inches with a standard deviation of 4.58 inches. Use this information to determine if the heights approximately follow the 68, 95, 99.7% rule. And there are the data down there. So I'm going to go over to the whiteboard in a minute. We're going to review the 68, 95, 99.7 rule. But before you do that, if you have not copied and pasted the question in yet and it's got the data in there yet, you might want to stop the video and do that real quick and then come back. Notice you got to put the data inside of an R chunk. I've named it female height, so FH equals, and then of course C for column. We're putting in a single vector of numbers, and then if you want to do a little error check to make sure you got your numbers put in there correctly, you can come down here. We're going to need it in a minute anyway, so we could type in x bar equals the mean of FH. So it's a really good idea once you get done just to check your work. And the STD is equal to the standard deviation of the female heights. Okay, and so if I run that chunk, comes back with, hey, look at that, got the exact same numbers. You can look up here or you can look down there, but best to look up here because otherwise I have to echo them. But it looks like, yes, indeed, my standard deviation and my mean came out to be what was purported. Okay, all right, so I'll give you a sec here. Okay, you're back. All right, cool. So let's go over to the whiteboard for a minute and let's go talk about the 68, 95, 99.7 rule before we get started here. So that's an important rule. It is important in the fact that we use it all the time. But one of the things you got to be careful. That's interesting. Didn't mean to do that. Sorry about that. One of the things you have to be careful about with this rule is that it only applies to normal distributions. So let's go ahead and draw ourselves a normal distribution here. You should do this at least once by hand. There's all sorts of pretty pictures. There's a very pretty picture in the book of this. But if you draw it once by hand and label it, then hopefully it'll make sense what it's talking about. So play along with me here, okay? So we know the center of the distribution right here is at mu. And we know from our previous discussions that if I move one standard deviation either side of the mean, I'm at the inflection points on my normal curve. And so this position right here on the axes is going to be at mu plus a single standard deviation sigma. So I'm doing this for a generic normal distribution. This is a normal model with mean mu and standard deviation sigma, right? And then of course over here, this point right here, this is going to be at mu minus sigma. Now what the 68% part of the rule means is that if I was to come in here and do some shading in between those 2 points, in other words, if I come in and I shade, we'll shade this in sort of a magenta tone here, this magenta region right here, that 68% of the data fall in there. In other words, that 68% of our area is within one standard deviation either side of the mean. Okay, cool beans. Well, what if we go out 2 standard deviations? Well, hopefully you can guess before I even do it here, we're going to get 95% of our data. So if we go out to this position right here, roughly, and this position right here, roughly, and I'm going to say, okay, that's another standard deviation, so that's mu plus 2 sigma. And down here, this is down yet another standard deviation, and so that's down at mu minus 2 sigma. All right, and so what is true about this, or what was purported to be true, and it is that if you do that, if you move out 2 standard deviations either side of the mean, then let me just I'll outline it in this part here and then shade it down here, that that is the green part, boxing in the green on the other part, but shading it here, that the green part, that's going to be 95% of our data. In other words, between two standard deviations, we'll get 95% of the data. So let me draw an arrow out from there to there to help you see that, okay? And in the previous one, that 68%, that was from what? From there to there. Okay, now if I go out 3 standard deviations, notice that I'm getting out to rather the skinny part of the curve. There's not a whole lot of area left. In fact, we're going to have to go out to 99.7 so that we don't say 100%, okay? So if I go mu minus 3 sigma, or up here to mu plus 3 sigma, then we notice that that's going to be 99.7 of all possible outcomes occurred in that interval. And so what that means is if I come out here and shade that in yellow, that this yellow shaded region, if I tag that in to the green and the pink, right? If I put that in there with the rest of it here, then what that tells me is that almost all of the data occurs in that interval. In fact, I'm going to go like this and raise it up so we can get it up out of the way. So that's 99 point. Let me go ahead and do that in black because I can't see it. If I can't see it, and there's probably you guys can't see it either. So that's 99.7% of all of the data falls within 3 standard deviations of the mean. All right, so the 68, 95, 99.7 rule is a very important rule. We're going to use that as we move forward in the class. But one thing that keep in mind is really important. This is only for normal distributions only. It only works in a normal distribution. It does not work, this little rule of thumb does not work in a skewed distribution or any other crazy shapes. It only works in the normal one. Okay, cool. Now, what they want us to do is determine normalcy of our data, to decide whether our data is normal or not, because it goes both ways. If your data fits the 68, 95, 99.7 rule, then it can be inferred to be normal. In other words, if my data follows that rule, then it's a normal distribution. If it's a normal distribution, it goes the other way. If it's a normal distribution, then we know that 68, 95, 99.7 is going to work on our distribution. In other words, 68% of the data will be within plus or minus 1 standard deviation, 95% within 2 standard deviations, and 99.7 within 3 standard deviations. Okay. So what they've done is they've given us some data and they've asked us to determine normalcy, whether we can infer a normal model of our distribution based upon whether or not it fits the 68, 95, 99.7 rule. Now, if this was the first time that we were to do this in R, it would be a fair amount of work, but we have actually done this once already. We did this back in the previous lab. So I'm going to go in and open up my previous assignment 2, go open up the RMD. See, I'm coming over here and just opening up assignment 2. And if I go into assignment 2 and I scroll down to the lab that we did in assignment 2, you'll see that there was some code in there. Here we go. Yes, there was some code in here that says, now on your own, be creative. If you remember that, part 3 of the lab. We're going to go in and we're going to steal that code. We're just going to go in and grab all of that. Okay, so we're going to go copy, and we're going to come back in here to assignment 3, and we're going to come down here. Let's go ahead and get rid of what I did a minute ago, and we're going to paste that in. Actually, I'm going to have to redo what I just did, but that's okay. No worries. So we know the code's the same, okay? So I pasted in the previous code. Now, why did I do that? Well, because remember, we did this already in problem 3 in lab 1, where we found how much of the data fell within plus or minus 1 standard deviation. So we can reuse this code. It's one of the beautiful things about code is that you can reuse it. You don't have to build it new every time. All right, a little bit different though. First of all, we need not find the mean of female data weight from that CDC data set. That's not what we're looking for. Ours is going to be from the data that we just banged in up here. In other words, it's going to be FH. So we need the mean and the standard deviation for FH. So I'm going to edit that code to mean that. And then down here, remember how the subset command works. The first thing in the subset command you need to know is where am I getting my data from? Well, in this case, it's not a data frame, it's a data vector. It's a single column. If you go back up here and take a look at FH and values, you'll notice that it says, hey, it's a single variable with 25 entries in it, and it gives you kind of an example of them. All right. So every place we see the F data $weight, we're just going to put FH because we're not in a data frame. We're in a single vector. That's one of the main differences between the code that we wrote and what we're going to fix up right now. Okay, so replace every place we saw with that. Now there's one other thing that we need to do. Dimension infers that you have more than one dimension. In other words, it infers that you have like a data frame, 2 dimensions, and you're going to get back 2 numbers. Well, in the case of a single vector, you don't use dimension to find out the number of items in it. Use length. And if there's anything tricky about this whole process we're doing, that would probably be it right there. Okay. We need to put in length. What length tells us is the length of the vector. Okay. And again, change that from F data to FH because we're defining everything in terms of FH here. So let's go through and read the code before we get started and let's see if it makes sense, and then we'll run it. So FH, first thing we did is we defined our vector and we entered in all of the data points. And if you have not yet done that, please go stop the video and go do that, okay? So FH equals C, that's for a column for our vector. And then down here we defined X bar. We assigned into X bar the mean of the FH, and we assigned into STD the standard deviation of FH. And now we're going to create a new variable called one standard deviation. And one standard deviation is going to be a subset of our previous vector FH, where the FH's are going to be greater than X bar minus 1 standard deviation, and the FH's are X bar less than 1 standard deviation. Okay, so let's go back for just a second here, back to our drawing. What I'm saying is that I want to get the values that fell within 1 standard deviation. So that piece of code, what it's going to do is give me all of the heights that fall into this interval right here. It's going to tell me everybody that's between plus or minus 1 standard deviation. So this 1SD variable will contain just the women's heights that fell within 1 standard deviation of the mean. All right, so let's go back into RStudio. Let's go execute this chunk and let's make sure it actually works. So run the current chunk, and there we go. Okay, so notice, let's come up here first. Notice 1SD, that there were 17 women's heights that fell within 1 standard deviation. There they are right there, okay, where our standard deviation and our mean was defined as before. And if we come down into the console, we'll see the output for length of 1SD divided by the length of FH. So that's, you could try this on your own, that's 17 divided by 25. Okay, because the length of the vector 1 standard deviation is 17, and the length of the vector FH for females' heights is equal to 25. All right, cool beans. So that's really good evidence, because that tells me within plus or minus 1 standard deviation, we're getting 68% of the data. So that's a good argument so far for inferring normalcy, but we can't stop there. We have to go and do the 2 standard deviations and the 3 standard deviations. So here's what you do. Just go copy lines, in my case 102 and 103, hit a return, make some space in your chunk, and then paste those in, and then we're going to come in and we're going to edit those. And we're going to say, well, okay, now this is going to be what? Well, it's going to be 2SD. So we'll make a new variable called 2SD, and we'll come over here and put a 2, and you can't use juxtaposition. RStudio is like every other programming language in the world. You have to tell it what you meant. You can't just set a 2 there. You have to tell it that it's multiplication, and you have to put an asterisk in there. So you'll get a funky error if you forget to do that. Be sure and put the asterisks in, all right? Okay, then we're going to come down here, and we got to change our 1 standard deviation to what? 2 standard deviations. All right, so let's go run our chunk again, make sure I didn't make any typos in there. Looking good. Okay, so within 2 standard deviations, we're getting 96% of our data falls in there. So, so far, looking like real close fit for a normal distribution. Okay, so let's go ahead and grab 2SD, bring it down here, paste it in, and we're going to change it, strangely enough, to 3SD. And so again, it's the female's height. The subset of that we want is going to be what? 3 standard deviations either side of it. So I'm going to change those to 3s, and then come down here, and I don't want the length of 2 standard deviations. I want the length of 3 standard deviations. So one more time, let's go ahead and run our chunk. And it at 99.7% rounded off comes out to 1, and so looking pretty much like it fits very well. Okay, so our response here is, they're asking us, how does it look like with respect to following that rule? And this data appears to follow the 68, 95, 99.7 rule very well, which infers the data is normally distributed. Okay, so just for grins and giggles, even though they didn't ask us to do this, let's go ahead and do a hist of FH. Well, if we do a hist of FH, oops, come back up here, my bad, and go ahead and execute that chunk, we get a distribution that looks not quite unlike that. Let's go ahead and zoom it so we can see it in all of its glorious detail. We'll go and make it up a little bigger there. And, it looks like it's roughly bell-shaped, and that's, you could infer there's maybe a bit of a skew to the right. There's maybe a slight bit, but that's okay. This data looks like it is really, relatively speaking, pretty well normally distributed. Okay, now there is one more plot besides the hist that they've shown us, but they didn't talk to us how to actually make one of these in R, and that's the QQ, or the quantile plot. This is the normal probability plot. You put in QQ norm, and then you give back FH again. And if we run this again, run our chunk one more time, that's the normal quantile plot, or the normal QQ plot is what it's called in many books, okay? And you see that, again, it's got a very strong linear trend to it. So again, good inference towards having a normal distribution. So if I was to just look at these two pictures here, I have roughly a bell-shaped distribution. My normal QQ plot looks like it's approximately linear. So based upon those pictures, I would say that, again, I have a roughly normal distribution, okay? That approximating this distribution or modeling this distribution with the normal distribution would be a good idea. It's okay. All right, so hopefully that helps. That obviously was the hardest problem of the lab, but maybe not for you. Maybe you found that one interesting and fun. I hope you did. So again, any questions, please post them up to discussions. I'll get back to you as quickly as I can, and I do take requests on videos. So if there is a problem that you need to see a video of, please let me know, and I will take care of that as quickly as I can for you.